Good morning, everyone. I hope you can hear me. Can someone reply if they can?
Good morning, sir. We can hear you.
Okay, good. Thank you. All right. So today we are going to talk about scheduling. We have been I've been talking about it very briefly before that. Okay, this is the high level policy and so on. So today we'll see things a little bit more in detail. So, what did we do in the last lecture? We looked at some mechanisms, and they are the low level things and about how to run processes smoothly. And one example was of that was context switch. Let's say. Okay. And today we'll look at one high level thing called schedulers. So this is a policy, and this is going to be about which job to run and when. Sorry, which job to run. When. Okay, good. So basically, we had encountered these questions that okay, like what happens when a job finishes IO, and then now it's IO is finished. So whether the OS should run this job or it should continue with the job which has been running previously, and so on. So actually, this turns out that not turns out actually the scheduling problem is actually not just about computers. It's in any supply chain or any operations management thing, this will be required. That okay, which who does what and when, right? So origins of scheduling is in operations management or supply chain. Okay. And so basically, wherever we need some efficiency that is tied with scheduling. So you can imagine like if you have a car factory and then like you want to different parts are being assembled by different people and then you have to combine and there will be some things which have to be done first and later and so on. Being scheduled. Okay. So, what is going to be the question, or what we'll be addressing today mainly? So, today's question is yeah, this is okay. So, first we will see that what is going to be the framework for studying these scheduling things. So, so you need to put things in a framework before you can formally study them, right? So, Okay. And so is it, yeah, okay, good. So first question is, what is the framework for developing scheduling policies? What are the assumptions? What is the metric? What are the metric? And what are some basic approaches? So these are the questions that we'll be addressing today. Okay, good. So first thing that, okay, we need to design the framework for developing the scheduling policies. So we need to define a certain things, and then only we can talk about, okay, which scheduler does what and so on. So a few words. So like generally the collection of processes to be run should be called the workload. Okay. And the more we know about workload, better or more fine-tuned scheduling policy will be. So, I mean, if you are going to run some processes, if you know what they are going to do, if you know what they involve, then of course you can like tweak your scheduling policy accordingly, and then to suit their needs. Okay. And another thing, like the processes to be run in scheduling context, they are generally called jobs. Okay, so I'll be using like jobs today throughout the lecture. Okay, good. So now we have the like words or the definitions in place, and let's talk about the assumptions. So we'll start with certain assumptions and we'll like relax them as we go along and see like which one of them makes more sense, or like what happens when we relax some of them, etc. Okay. So first assumption is going to be each job runs for same amount of time. So this is just like, so these assumptions are going to be just the basic starting point to talk about schedulers. And as I said, of course, like, they are not what happens in reality, but it will be good to start with these assumptions so that we can get some basics out there, and then we'll relax them as we go. Okay. Second assumption is that all jobs arrive at the same point, same time, point of time, whatever you'd like. And once started, job runs to completion. So this means that if we start a job, then we finish it. No IO done by any job. Again, this is also a very unrealistic assumption, and we know how long a job will run for. Okay, so these are going to be our assumptions, and the last one might seem especially like unrealistic because when we start a process, we don't really know how long, but okay, we'll see how to deal with these things. Okay, so and yeah, especially for the last one, if like so you guys might have heard about this thing called halting problem. That given a program, whether another program can determine whether this program will halt or not. And this is just an aside. Have you heard about this? Have you been taught about this in any course?
No, sir.
No answer.
No,
No, sir. Okay, then I would like urge you to go explore about this. Like, just it is a very famous problem which was shown to be undecidable. That no computer can actually solve this problem. So if you're given a program and you want to write another program, which when given as input, this program wants to just tell whether this, like, so you have program A and program B. So you want to write program A, which tells whether program B goes into infinite loop or not. And this is impossible. So you cannot write a program which can check whether a program goes into infinite loop. So it's
So
a
is
very
this
nice.
NP hard?
No, it's not NP hard. It's undecidable. So NP hard problems are decidable, or any any problem in NP. I mean, it's NP hard. Yes, sorry, it is not NP complete. It is any problem in NP, of course, can be reduced to halting problem for those who understand this. If you don't, it's fine. It is NP hard, but it's much harder than NP hard. It's undecidable. So like you cannot decide it. Yeah. So NP hard problems generally when we talk, it takes a lot of time to decide them, but this problem cannot be decided irrespective of how much time you take. So that is the like funny thing. I mean, that is not the part of the lecture, but since I'm generally interested in theoretical computer science, I would like urge you to go read it. It's quite nice. The proof. It's a very cute proof. It's a short proof, like half a page or something, but it's very nice. I really like it. Okay, good. So yeah, that came because we were making these assumptions that we know how long a job is going to run. So basically, we generally do not know how long a program is going to run, and that has been theoretically proven. Okay, good. So that was the first question. Okay, the second question. So the framework is going to be, of course, that there are going to be jobs and there are going to be certain assumptions, and now the metrics. So what is a metric? So what is a metric? Anyone? You guys are in math. What does a metric do? Any metric?
It measures how
Yeah.
well the algorithm is.
Yeah. So it used to measure something. I mean, not just in case of algorithms, you have like generally in math also you have like these measurement things like you have L2 metric or different sort of metric like Manhattan and stuff like that. Okay, good. So now we want to measure how scheduling policy performs. Okay, so we want to define metrics for that. Okay, so what can be a metric which can make sense? In case of scheduling. Any guesses? Or, I mean, just say what you feel that, okay, now I want to design a scheduler, and how can I measure its performance, or how can I say that, okay, this is a good way to measure its performance?
total time to complete all jobs in the workflow.
Sorry?
Total time to complete all the jobs in the workflow.
Total time to complete all the jobs. Okay, so, okay, option one, let's say. total time to complete all the jobs.
Waiting time of the job.
Sorry?
Waiting time of the job.
Waiting time of the job. That's a good one. We'll come to that. Okay, so let's look at this one. So what is scheduling? So this question was asked. So is that answered by now? That scheduling is about which process to run when. Dharmendra? Dharmendra, can you hear me? Okay. All right. Okay. So Dharmendra asked this question that what is scheduling in the chat, and I hope that question is answered by now. Okay. So good. Let me just. So good. So total time to complete all the jobs. So this I would say is okay. Yeah. This I would say is not going to be such a good one, because if you run one job after the others, and then all jobs take as much time as they would have wanted to take, then like it doesn't matter which job you run first, second, or third. It's not really going to be. It's not really going to matter. Total time to complete all job is going to be the same. Like the scheduler does not really uh, alter this metric, let's say. Okay. Whose suggestion was that, by the way?
Mine, Arpit.
Okay, Arpit, yeah. So you get why this might not be a good idea, right?
Yeah.
Okay, good. So option 2, as someone said, was waiting time. Right? That how much a process has to wait. After arrival. Okay. And this is a good one, and we'll come to this because this is basically, this decides somehow the fairness of the scheduler, that okay, a process should not have to wait very long. So yes, this does make sense, and we'll come to that. So let's call this actually, okay, we'll come to that, it is called actually response time. So this is measured in terms of response time actually. And this is going to be time at process is first run minus time at which the process arrives. Okay. But right now we are going to concern ourselves. So this we'll see, and then another metric is how much time does it take for a job to complete after it has arrived. Okay. So that's called turnaround time. Okay, so let's write it a little bit more formally. So, let's say T turnaround is equal to T completion minus T arrival. Good. So this is for a job. And generally, what we'll do, we'll talk about the average turnaround time. Average. So basically, we just like take the sum and divide by the number of jobs. Good. So now, but we had certain assumptions, and the second assumption was that so due to assumption 2, all the jobs arrive at the same time. So basically, instead of writing the whole sentence, just write that T arrival is equal to 0 for all jobs. And hence, T turnaround is equal to T completion. Okay, good. And we'll be talking about the average turnaround time for the jobs that we'll be talking about. Okay, good. So, as I said, this is a performance metric. So this is about performance. This is not so much about fairness. And talks about how quickly a job completes. Okay. So this is a performance metric, but another can be fairness metric. So this was a fairness metric which was suggested by Shubhalingam. Did Shubhalingam suggest that?
Yes, sir.
Okay, so this is yeah. So the metric which was suggested by Shubhalingam is a fairness metric. Sorry. And we'll see that getting both these things like right might not always be possible. So getting performance and fairness might not be possible always. Okay, good. So we'll see why this happens. I mean, generally, so let me just say this in words that when we want performance, then we want jobs to complete fast. Then some jobs might have to wait a lot. Okay, and that will decrease the fairness thing because the waiting time, the response time will increase. But when we are trying to be fair, we are trying to give time to every job. Then, of course, the average time of the jobs which are going to complete is going to be larger. So this might affect performance. Okay. I mean, this is just like in one sentence, in a nutshell, I said, but you'll see how this works in practice also. Okay, so the first scheduling policy that we are going to look at is going to be first in, first out. It's also called FIFO. Okay, so this is like, yeah.
Sir, if the turnaround time is less, then the response time will also be less, right?
No, that's not. You'll see examples where like they differ and how they differ. So it will be
No,
better to work
but
with examples. Yeah.
sir, if jobs are done very quickly, then other jobs will have to wait less. So
But
these two can be done simultaneously.
okay, so let's like talk at the end of the lecture, and then if your question still remains, then I'll answer that. Okay. Because this is generally not possible, and you'll see why that is the case. So right now it might seem that these can be like achieved simultaneously, but we'll see that why it's going to be hard or actually not possible. Okay. So just like wait for a little bit. I get your question, and like of course this is a very obvious or like very natural question, so to say. But yeah, to answer that, let's wait for just a bit. Okay. Good. Okay. So what is first in first out? It works as it is named. So it schedules the job that arrives the earliest, or it schedules the jobs in the order of their arrival time. Okay, so I mean, this is just like whichever came first, there is a queue, and then like in the order they come, it just keeps scheduling it. So let's say A, B, C are jobs arriving at t is equal to 0. They all want to run for 10 seconds each. And let's say that, okay, A came, like B came, just because first in, first out needs to have an ordering. So let's say 1 millisecond after A and C 1 millisecond after B. So, I mean, so this is not going to affect the average times much, but this is just to have an ordering. Okay, good. So what is the scheduler going to do? So let's say this is 0, 10, 20, 30. It is just going to put A here. It's going to put, let's say, B here and C here. So what is the average turnaround time in this case? So what is the turnaround time for A?
10 millisecond.
10 seconds. It works for 10 seconds, let's say. Okay. And for B, oops, sorry. For B,
20 seconds.
yes, 20 seconds. Because they run for 10 seconds each, okay? Let's say. For C, it's 30 seconds. Okay, so what is the average turnaround time? A, B, and C. What is the average?
20 seconds.
20 seconds. Good. So this was just an example to like get you how to compute the average turnaround time. Okay, good. Now let's. So this was quite simple. All jobs arrive at the same time, and they run for the same time, and so on. Yeah. And is there a question? Okay, wait. My voice is echoing. That might mean that in the team have I? No, I'm muted there. All right. Okay, now it's not echoing, I guess. Yeah. Okay, good. So yeah. So now suppose we want to analyze this like slightly better, and this is always like this of course is not going to be the case. So suppose relax assumption one. So what was assumption one? It was about that all jobs arrive at the same time. So not all jobs arrive at the same time. No, sorry. Assumption one was all jobs run for the same time. So okay, so this is going to be our one exercise that we are going to do in this lecture, and in this lecture definitely, that we want to design now some workload where the current scheduling policy is going to perform bad. Okay, so now suppose not all jobs run for the same time, and we want to like increase the turnaround time of this FIFO scheduler. So suppose you have A, B, and C, and you have relaxed this condition that all jobs run for the same time. Then what would you do to make the scheduler perform badly?
So make the longest time job arrive first.
Exactly. So let's say A runs for 100 seconds and B, C for 10, and A arrives first. Okay, then what is the scheduler going to do? Then for like 100 seconds, it's going to run A. Then for 10 seconds each, it's going to run B and C. So T is equal to 0, 100, 110, 120, right? So what is going to be the average turnaround time in this case? 100 plus 100. So let's say like B and C also came here only because we have not relaxed that. 110, right? So this is called like convoy effect. Basically getting stuck behind, or small resource consuming things getting or lightweight things getting stuck behind heavy ones. Like, so in the book, they give the example that you are in a supermarket line and there is somebody at the front who has like a lot of stuff and is like, paying by coupons, their card is not working or whatever, and you're just stuck there, just waiting to buy your one item. Okay, good. And that's what is happening to B and C in this case. All right. So, so this is something where this happens. So suppose, in this case, they all arrive at the same time, and then there is another policy that we are going to see, which is going to be shortest job first. Okay. So, as the name suggests, this runs the shortest job first, then the next shortest, and so on. Okay. So now suppose this was the case. A runs for 100 seconds, B and C for 10 seconds each, and they arrive at the same time as it was an assumption. So we'll abbreviate as SJF. Okay. So then what is SJF going to do? This is t is equal to 0, t is equal to 10, t is equal to 20, and then t is equal to 120. Okay. So it is first going to schedule B or C. Let's say B, then it will schedule C, and then it will finally schedule A. Okay, because B and C are going to be shorter jobs. They run for the shorter amount of time. Okay, and what is the average turnaround time in this case? What is it going to be? Or tell me the summation. For B, how much it's going to be?
10,
10. For C
20,
and for A?
120.
So this is going to be 50 seconds, right? So last time, how much it was? 110, and now you got 50, so you got a lot of improvement over that. In fact, if all jobs arrive at the same time, and we have just relaxed the second condition that they just, or first condition that they might have different lengths or they might run for different lengths. In that case, so shortest job first is optimal. It can be proved that if all jobs arrive at the same time, then there is like SGF does as good as any other scheduling policy which might be designed. So this you can try to prove since you guys are, or a lot of you will be inclined towards mathematical things. So you can try to prove this. Sorry. But that is not going to be like, in this lecture, in this course, generally will not be proving things as it is a more applied, course.
So,
Yeah.
so what if B and C arrive at the exact same time?
Then it can decide arbitrarily, let's say. So if there are two jobs which arrive at the exact same time, then like it can break the ties arbitrarily. But generally this does not happen. I mean, there is some gap or whatever. Okay, so now how can we make this perform badly? So again, the same question. How can we make this scheduling policy to perform badly?
When not all jobs arrive at the same time.
Yeah, so relax the criteria, relax the assumption number, whatever it was. That all right. Yeah, so the second. To that all jobs arrive at the same time. So suppose A arrives at t is equal to 0, B and C arrive at t is equal to 10. That's it. Okay. So then what is this scheduler going to do? This is t is equal to 0. It does not have any other job, so it puts A first. And since all jobs run to completion because of our some assumption, and here t is equal to 10, B and C arrive here. Now it will put B, C later, right? So now what is going to be the average turnaround time? For A, how much it's going to be?
100.
B?
100.
So let's say 110 minus 10. 120 plus minus 10. 3. So this is going to be, I'm sorry, 310 divided by 3, which is 103.33. So this performed quite badly, right? All right, so now we will not, so we saw that, okay, if we start like this and we uh, run a job to completion when we start, then we are going to get stuck behind jobs which are going to take long time, and then there is no way to like remove them. So now we'll like relax another assumption that a job has to run to completion when it's scheduled. Okay, so it's called shortest time to completion. STCF. Okay. So which requirement we are going to relax? That jobs run to completion. Whichever number it was, maybe 3. After being started. So what now we'll do, we can we have seen the mechanisms of doing that, okay, what if we want to like stop one job from running and uh, like run another job and so on. So now the scheduler will make use of those mechanisms that we saw in the last lecture to like do this. Okay, good. So now the scheduler can stop A or preempt A. And decide to run something else. Very good. So what is going to be the policy? Whenever a job enters, the system scheduler determines which one has least time left or will be completed first. I mean, not completed first. So this, I'm saying this, like, this is like abuse of, whatever this way of saying this. Of course, completed first will have to be defined in terms of what actually is happening, but in loose terms, I'm saying this. So scheduler determines which one has least time left. That is more precise. That okay, all the jobs they have, the scheduler knows how much time they are going to take, and it's going to decide that which one has least time left, and then schedules that one first. And so on. Okay, good. Okay, it says working offline, but it seems like it's working. Okay, so in that case, so look at the earlier case that, okay, A again runs for 100 seconds, arrives at t is equal to 0, B for 10 seconds, arrives at t is equal to 10, C for 10, arrives at t is equal to 10. So now what is going to happen? That so A ran for, so this is t is equal to 0, say 10, 20, 30. So at first just A was there, so the scheduler ran A for 10 seconds. But now B and C come into the system. Okay, so now the scheduler determines, okay, A is going to take 90 seconds to complete, but B and C are going to take 10 seconds to complete. So it will schedule one of B and C. Let's say B. Then B finishes. Now here A still has 90 seconds left. C has 10 seconds left. So schedule C here. And now it is only left with A, so it will A, right? So it will finish at 128. Good. So what is the average turnaround time in this case? What is for A?
120.
120 minus 0 because A arrived at t is equal to 0. For B,
20 minus 10.
20 minus 10. And for C,
30 minus 10.
30 minus 10. Okay. So this is 120 plus 10 plus 20. That is going to be 150 by 3 is equal to 50. Okay. In fact, now with these assumptions that you know how much a job is going to run, you can actually say that this is optimal. So with these assumptions, I think 4 and 5, one can say, one can prove actually. HTCF, yes. Okay, good. For this metric, for average turnaround time. Again, like those mathematically inclined should try to prove it. It's not very hard. You just have to make a like sort of adversary argument that, okay, like, you know, this does as good as any other scheduling policy. And like you might have proved for greedy algorithms. So this is some kind of a greedy algorithm. And you can show that this works. Okay, so now as we talked about earlier, turnaround time might not be the only metric that we want to consider, but also, you want to, like, decrease the wait time. And that becomes quite, um, quite important, especially in case of like when there are many users and they want to, perform a job on a computer. So suppose many users are there, we don't want to make them wait a lot. Wait too much. So we want to minimize this thing called wait time, or as I said, we'll call it response time. So this is going to be our new metric. And what is T response? is equal to T first run minus T arrival. Okay. And now let's look at this one. So let's take the response time for this. So, okay, so I hope you can remember that how this was done in the case of when STCF was given A, B, and C in this thing. So, what was the response time for A?
0.
0. For B?
0.
For C?
10.
So, average response time is 3.33 seconds. Okay, good. And actually, it will turn out that this is quite a lot, and STCF is not very good for response time metric. Okay, because if, let's say, 3 jobs arrive at the same time, then the last job, which is going to be the longest, will have to wait for the first 2 jobs to complete, and then only it can get the CPU. Okay, good. And yeah, so generally, so that's what I was saying, that if it is good for response time, good for turnaround time, then it is going to be bad for response time. Okay. So now we are going to look at a scheduler that is good for response time. So aim is going to be to build a scheduler good for response time metric. And that's going to be this thing called round robin. Okay. So instead of running, yeah, is there a question? No? Okay.
Yes,
Instead
sir.
of,
I had a question.
yeah.
So, what was the problem with STCF with response time?
That the response time was bad. It was 3.33, and we'll see how it can be like,
So, isn't that the best we could do in that case? Because only one job had a greater than 0 response time.
Yes, but the greater than 0 can be reduced. So it is 10 seconds, but we'll see. Like, just wait for a moment and we'll come to that. Okay. So instead of running jobs to completion, so we'll abbreviate it as RR. Okay. So RR runs jobs for what is called a time slice. Okay, good. And it is also called like scheduler quantum sometimes. Okay, and then switches to the next. And so on. Okay, good. Keep doing this till all jobs are finished. Okay. And just like one thing to note that this time slice should be a multiple of the timer interrupt cycle. So there is a timer interrupt thing that I described in the last lecture, that the OS will have a timer which will interrupt the whatever process is running after like every so many seconds, right? Or milliseconds actually, not seconds. That's going to be too much. So if if this is suppose 10 milliseconds, then this can be 20, 10 or 20, 30. I mean, some multiple of 10. Okay. So now, I mean, yeah.
So what was the queue? What was the ordering in the queue?
Ordering in the queue can be in the order the jobs came.
Okay, sir.
Okay. So, but again, since the aim here is going to be very different, you'll see that, the ordering will not matter so much. So suppose now A, B, and C come, want to run for 5 seconds each. Okay. And shortest job first or STCF will run 2 jobs before scheduling the third. Right? So what is the response time? Or let's say average response time. It's going to be for the first job 0, for the second 5, for the third 10, and then 3 is equal to 5 seconds. Okay. Now suppose there is an RR scheduler. So with, let's say, time slice of 1 second. So what it will do, it will run A first for 1 second. It will run B, then it will C, A, B, C, and so on, and it will take 15 seconds total. Right? And here everything will finish. So what is going to be the average response time? Zero plus 1 plus 2 over 3 is equal to 1 second. Okay? And if we reduce the time slice, let's say 0.5 second, then average response time will be, so again, this won't be 0, 1, this will be 0.5, this will be 1, and so on. So this is going to be 0.5 plus, 0 plus 0.5 plus 1 over 3 is equal to 0.5 seconds. Okay? So as you see that if you decrease the time slice, then the response time goes down. So shorter time slice implies better performance with response time metric. Okay, but you cannot, like, there is of course a caveat, which is cannot decrease the time slash too much. Why? Anyone?
It will become less than a timer interrupt.
Yes, but there is one more reason for that.
Expensive
Some
task.
overhead in
Sorry?
there is some overhead in context switching, so we don't
Exactly.
do that too much.
So that is more important that suppose for every timer interrupt you are doing this, then like every time you switch a job, you have some, it will take some time. So if you decrease the time more than that, or if you go to that level, then that time will dominate the whole running time, right? Context switching will dominate the running time, which you don't want. You want like jobs to run for a certain time, and then context switch should be fast enough. And then like yeah, suppose you are switching context like every 2 seconds, then like nothing is being done actually. All the time you are just switching context. Okay, so like there will be this trade-off that it should be short but not too short. Okay. Okay, but what is going to be the turnaround time in this case? The metric that we were looking at earlier. So what is going to be the turnaround time for A? So A will finish somewhere here, right? So this will be A, this will be B, this will be C. So let's say 12, 13, 14, 15. So what is the turnaround time for A?
13.
Okay, so 13 plus 14 plus 15 divided by 3 is equal to 14. Right? And in case of SJF or these things, even if we use like FIFO, then the turnaround time was going to be like quite less. Right? So it was not going to be 14. So let's say FIFO or shortest job first or shortest to completion first, average turnaround time. So for, or let's say less than or equal to something, 0, something will be, sorry, not 0. Something will get scheduled first. So 5 plus 10 plus 15, let's say, over 3 is equal to 10. Okay. So this performed even worse than FIFO. And this is, of course, like, I mean, not obvious, I would say, but this is definitely the result of jobs being stretched out. Okay, so they don't finish fast. So turnaround time increases. I mean, if you just do the jobs in bursts, then of course the turnaround time will be less, right? So that is the problem, that if you want to have fairness, so this will divide CPU among many jobs. And turnaround time will increase. And if you want performance in terms of turnaround time, then you would want jobs to finish fast. but some others will have to wait. So this is like unfair, not fair. So this is like always a trade-off between a scheduling policy, in a scheduling policy between fairness and performance, that what it is going to go for. Okay. So does that answer your question, Shaurya? You were asking before, right? Why can't we get both?
Not really, sir, but yes.
Okay, so I mean, you can like spend like okay, but can you formulate what you're not getting right now so that I can like try to convince you a bit more, or you would like to take it on your own?
Like, sir, I don't think it was my question.
Oh, okay, it was not your question. So somebody was asking earlier. Who was asking?
Yeah, it was my question.
So
Girjesh.
Girjesh, yeah.
Yes.
So Girjesh, does this now answer your question that how can we achieve like even shorter response times by time
Yes.
slicing?
Yes.
Okay, good. Thank you.
So can virtualization help?
I mean, all this is being done in a virtual way. Okay,
Like
so
in virtualization, every process can assume that it has its own CPU. So the
that is happening in this case anyway. So all the processes do assume that they have their own CPU. So this is how we are achieving virtualization. These are the like mechanisms and policies which are going to like But when a process is running, of course, it is thinking that it has like the CPU to itself. So that is happening in this case. In all the cases, like it does not matter on the scheduling policy or on these things. So when a job is running, it thinks that the CPU, the CPU belongs only to it. Does it answer?
yes.
Okay. So Krishna asked how to compute these jobs runtime. As I said, we are not going to know that, but that is an assumption. So we are assuming we know them beforehand. Yeah. So that is an assumption, as Shaurya said, that is as an assumption that we have made. In fact, we have made another assumption that we are going to now relax. The fourth assumption that jobs with IO. So the fourth assumption was that okay, no job performs any input and output, right? So, but that's not going to be the case. Like all jobs do some input output, right? So actually, in the book, there is a very nice argument for why all jobs should do input and output both. So, like, why read the book? And it's quite nice. I mean, it's just a like two-line argument. It's a like but it's quite logical argument. Okay, so now there will be jobs which will perform like input output, and we have not considered those things. That what to do when a job, because we saw this question actually earlier that okay, a job performs. So there are two situations. A job requests IO. Now it is blocked. So we had seen these process states, and one of them was blocked till it gets a response. Now scheduler should schedule another job there. And now suppose when IO completes, then scheduler needs to decide what to run. Okay, good. Now, suppose there are, so let's take an example. There are two jobs, A and B, both run for 50 milliseconds. For 50 milliseconds, but A requests some IO after running for 10 milliseconds. Every 10 milliseconds. Okay, good. And B does not do any such thing. B just runs for 50 milliseconds and exits. I just said that I mean all jobs perform, but just for this example, we are assuming that B does not perform any input output. Okay, good. So now suppose we schedule A first and B later, because we say that okay, both run for 50 seconds and then we should do this. Then that does not make a lot of sense, even if we are talking about turnaround time, because I mean A will run, and suppose the IO also takes like 10 milliseconds. So this is 10, then A waits, then again A runs, then A waits for 10, so on, and then finally A finishes, let's say. No, it has run for 40 only. So let's say, yeah. So it finishes at 90 and then B runs for 50 and 140, right? So this is not, so of course the scheduler should take into account that A is going to make IO requests. Okay, and so what is going to be the solution of that? How does it solution? How does the scheduler take this into account? It takes every 10 milliseconds of sub job of A that makes IO request as an independent job. Right? So this is what so it will slice up A into like 5 sub jobs and look at them as independent jobs. Okay. So now this job will not even be ready at this point, right? Because it can only be ready when it receives the thing. So now let's say we are implementing a shortest to completion first. Okay. So then there will be A, which will get scheduled because it's only 10 seconds long, because it is now being treated as independent job. Then now the second job is not even ready for A. So now there is B, which takes 50 seconds. So B will get scheduled while the IO is being done. Then now the job of A comes, that now takes only 10 seconds while B has 40 seconds left. So that gets scheduled and so on, right? And finally at 100 seconds they finish. Okay, so this allows for overlap while input output is happening. Right? So I mean overlap in the sense that some other process is running while one is waiting for input output. Okay, and this is like, of course, better utilization of resources. Okay, and this actually makes sure that if there are some interactive processes, which want some response from input or output frequently, then they also get to run frequently, because then they're they are divided into sub jobs, and those sub jobs anything, you wouldn't want a word editor to wait for a long time because you're typing something and it needs a response time every time. So every sub job of it, whenever it needs a response, it will be treated as a short job and will be scheduled, right? So they get scheduled frequently. And the good thing is that even though they get scheduled frequently, it does not alter the performance much, because while they are waiting for IO, other jobs are running. Okay, good. So now we are, so this was about input output, that, okay, how do we made this assumption about input output that none of the jobs make input output requests. So we relaxed that also, and then we saw that how one of these schedulers can do that. So for example, shortest to completion first. And so actually shortest to completion first, or some hybrid of these things is going to be present in every system. We still have one assumption left. We assumed that we know how much job, how much time a job is going to take to complete. So what if we relax this? And that's what we'll see in the next lecture, when we'll talk about multi-level feedback queue. And that is going to be quite close to a full-blown scheduler that we see in some of the modern day computers, right? So today we saw some scheduling policies like FIFO, shortest job first, shortest to completion first, and round robin. And then we saw how to incorporate IO with these things. We saw the trade-off between performance and fairness. And yeah, that's some scheduling basics for you guys. And yeah, next time we'll talk about how to relax this requirement that we had. And then we'll see how a multi-level feedback queue works. So any questions about today's lecture or anything? We are almost out of time, but we might have time for a question or two.
Sir?
Yeah.
Sir, for the IO, IO is being done in the background, we're assuming B is being scheduled in its place.
Yes.
Then who is processing the IO if the CPU is doing B?
So IO generally does not need a processing, right? So what does it mean for waiting for IO? So a program now is running and it requested something from the disk, for example. So there's no process. So the disk access speed is going to be the bottleneck for that process. There is nothing to be processed here. First, you have to bring the contents of the disk. So IO is generally slower than the processor. Now the processor is sitting idle at that time.
Okay, so the disk request part is included in A.
Yes, of course.
Okay.
So after A requests, then now while it's waiting, then it will be preempted and then B will be scheduled. Okay. Good. Any other questions? Okay, good. So as you are seeing that right now we are discussing at a very high level that okay, these jobs will be scheduled this and that, like in this way or that way. So we are not talking about the details and so on, and that is the difference between like a high level thing like a policy and a low level thing like a mechanism, which like somebody had asked on Piazza as well. Okay, so if there are no more questions, then thank you all for coming today, and I'll see you on Thursday. Or if there is any question, like just take a moment to ask. Okay, thank you then. See you guys on Thursday.